Welcome back to Data Science at Home. I'm Francesco, and in this episode, I would like to clarify a few concepts related to the how to serve large language models at scale. This is a question that has come many times via emails to all the followers of the show, and so I decided to make this episode to unveil kind of, look behind the curtain, as they say, about this technology that definitely looks like magic, but in fact it's not, because this is just computer science to its finest. So I prepared a bunch of slides just to follow the conversation, in an easier way, and explain a bit what happens every time that you type a prompt and you get these magic responses that look like human, in fact. So yeah, let's get started. How LLMs are served at scale. Well, the very first thing that we have to know is by a bunch of numbers, okay, which are basically these ones. So the typical model weight size in floating point 16 bits is approximately, well, it's in a range between 100 and 500 gigabytes of space, depending on, of course, which model you are chatting with or which AI assistant you are using for your tasks. Then we have, of course, the hardware aspects, which is the typically NVIDIA H100 GPUs. Each model typically has between 8 and 16 GPUs at its disposal. And what I'm saying here is essentially the specs of one single node, right? I will explain a bit what a node is in a minute. The typical context window, this is something that keeps changing, of course, 200,000 tokens. And of course, every model kind of in a marketing spec, it's something that it's becoming larger and larger, which is essentially, the size of the context that each request can access to. And of course, the larger the window, the more information is in that prompt, and therefore the more accurate that generated answer can be. Now, there are three essential problems that need to be solved whenever you deal with serving a large language model in production. Definitely latency is one of them. So essentially it's the delay that the user has to wait until the first generated token. Then we have the throughput, which is another important measure or metric in computer science, which is typically the number of tokens, words, bits in general in the unit of time. Definitely memory, which is very much associated to the context window. So it's literally speaking what the large language model can remember. And I quote remember, because I will explain what actually memory is for a large language model before generating that answer. And finally, the cost, which is also a very important factor, because if you start cranking up all these metrics to the best possible, the cost, of course, starts increasing quite dramatically. And this, of course, means that the provider of that artificial intelligence for the users will become, will have less and less margins. So probably what you will be charged is gonna, increase exponentially. So this is a variable that you definitely need to take, to control and to keep as low as possible. Of course, hopefully without affecting the performance, the accuracy, the reliability of the answers that you get from the model. Now, here is the another concept that I want to clarify before giving more details about what happens when you hit that button and start, ask a large language model to generate something, is the model parallelism. So there are two essential forms of parallelism, and this is not anything specific to large language models. This is something that goes beyond large language models, and it's the typical parallelism that we find in computer services since ever, since way before the 90s. Well, when you speak about services in production at scale, there are two factors that you want to take into account, which is so-called horizontal split and vertical split. So the first is you typically referred to as tensor parallelism, and the second, pipeline parallelism. So what is that? Well, in tensor parallelism, essentially what you do is taking the weight matrices, basically the weights of the model, and literally spread it across a certain number of GPUs, right? Now, each GPU, of course, can handle a slice of every layer at the same time. So this is good because it reduces the per layer latency, simply because you have multiple GPUs, each taking care of a single slice. And then, of course, you need to find a way to recombine these things in parallel. The second form of parallelism is the vertical split, in which the transformer layers, and I'm not going to go into the details of what a transformer is, but essentially it's like the core, the functioning core of pretty much any large language model. You know, the GPT family of model, they are all based on the concept of transformer. And transformer has layers, and these layers, so different layers are assigned to different GPUs or entire nodes. So remember when I said, when I gave you these numbers, well, these numbers are essentially specific to each single node, right? Think about as a one standalone machine in a cluster of nodes that, of course, cooperate to serve requests for millions of users, probably. Now, what happens here is that the output of layer n is typically fed directly into the next layer, on the next device, on the next node, and so on, right? So these are the two forms of parallelism that computer engineers take into account for, again, any type of service at scale, not just large language models, all right? Now, the other concept that I want to clarify is KV cache and batching. So what is this? Well, during token generation, we have so-called attention keys and values. And this is, again, another important aspect of the concept of transformers, right? So what happens here is that we have the attention keys and values for all the previous tokens are cached somewhere. So they are saved, they are stored somewhere, typically in a GPU memory, which, by the way, is quite expensive with respect to CPU memory, which is also expensive recently because, RAM prices have increased quite dramatically in the last months. And essentially what happens, well, with this concept, the concept of caching is pretty much the same for, again, any production service at scale. That is simply, is a very simple concept that says, hey, if I saw these things before, I'm not going to recompute them again. I'm just going to fetch them from the cache and keep reusing them and continue the computation over the things that I haven't seen so far. That's what a cache is, right? So what is the problem here? Well, the problem is that this KV cache grows as the sequence grows. Okay, so it grows with the sequence length. And this means that it can consume more and more memory than even the model waits for long conversation. So the longer the conversation, the more you are caching and the more this cache grows. It's a very simple concept, right? There's no magic. There's no free lunch, as they say. Now, what happens with continuous batching? Now, there are several solutions how to do batching and how to use that cache. Well, the most trivial one, the one that was definitely used at the very beginning of, when large language models were actually a novel thing. It was just waiting for the full batch, then process the full batch, and repeat that, right? Now, if you consider this approach, which again, it works, but it's like naive, it's like not optimized. What happens is that before you see the first generated token, you have to wait for processing the entire batch, which of course increases the latency. And this might make the experience of chatting with an LLM, quite inconvenient, because, you would be there waiting, and then all of a sudden you see the first token being generated. It's quite annoying, isn't it, right? So that's how they improved on that. And they said, okay, but we can have so-called continuous batching. And what is continuous batching? Well, this is a very smart thing, because all the requests are essentially inserted and removed from an in-flight batch dynamically. So basically, as one user's generation terminates, another request fills the slot. And this means that there is this continuous form of batching, which, as a result, keeps the GPU always working. It keeps the GPU always busy computing stuff. It doesn't sacrifice the per user latency. And of course, it's more efficient because, if you are paying for a GPU in the unit of time, you're actually using that GPU almost all the time, right? You don't want the GPU to sit there and do nothing, right? You paid for it. So yeah, these are the two concepts. Now, there is also paged attention, and I'm reading. This treats KV cache like virtual memory with pages. I wanted to write this down just to make that comparison for those who know, for example, operating system design and operating system level memory management. That's exactly the same, all right? These concepts, again, are not new. I don't know why people think these concepts are new, but they're not. Like, this is what we have been doing for decades with pretty much all the internet services and services that have to be scalable and served to millions and millions of users. So nothing new there. It's just a fancy way of, speaking about technologies that already exist. All right, so let's move on to the stateless illusion. Now, this is something that I definitely want to clarify. What is this? Well, when you type a prompt, okay, you are chatting with a large language model, you think, you have the feeling, you have the impression that the large language model is kind of a human that remembers things and looks back in its memory and responds to you by remembering, right? The concept of remembering, which is a very powerful concept because it really looks human, but it's definitely not. And I'm telling you why. Well, the first thing to say is that the models that you are dealing with have zero memory, all right? There's no concept of memory whatsoever in a large language model. And this memory concept or capability is a trick, is an illusion that is performed by other actors, in particular your browser, okay? So in fact, we have your browser, your client, in case of a browser in case of an agent, whatever, a CLI, whatever you're using for sending that prompt to the large language model. So what happens in the browser, if we take the example of the chatbot, well, it stores message history locally, typically on a standalone database, IndexedDB and SQLite, whatever. Then there is the application backend. The application backend is an interesting thing because it persists the history of your conversation to a database, all right? This is the main reason why you change computer or you use your mobile to chat, or then you go back home and you use your laptop or whatever, and your conversations are there, even if you just log in again and your conversations are there, simply because the application backend has stored them, has persisted all your history in a simple database. Now, what happens next is that you have the inference API. So the time in which you click, you type, you click, and you're sending that prompt to the large language model. You're using the inference API, right? Well, what you're doing there is simply sending a prompt and rebuilding that on each turn. So what you're doing is at every turn of your conversation, you're sending back to the inference API the entire thing, right? Now, of course, there are optimizations that allow you not to send the entire thing all the time, but stick with me for a while, because the way it works, I will explain in a few seconds. After the inference API, well, it's time to hit the GPU cluster. That's where the actual tokens are generated, right? So you process this token in the cluster, and then, of course, you use the KV cache and you generate tokens and you return them as a response back to your browser, assistant in general, right? Now, what happens in terms of timeline is that at every single request, okay, every single request, you have the system prompt, then you have your input. So when it's your turn to speak, to chat, then you have the assistant response, so the AI that returns something. Now, when you chat again, it's your turn, number 2. It's the second turn of the user. Now, all these things get appended, okay, one after the other. So you have system prompt, user turn 1, assistant turn 1, user turn 2, assistant turn 2, user turn 3, assistant turn 3, and so on. So this means that every time you type the current message, the prompt that you're actually sending to the inference API is the list, the history of all the messages in the past conversation plus the current message. Okay, I'm sorry to kill the magic, but that's exactly what happens when you chat to a large language model. There's nothing else, right? So what happens there is that, of course, there are many forms of optimization that you can do, especially using the KV cache, because at this point one can say, yes, but I don't want to recompute user turn 1 plus assistant turn 1 because guess what? I already have this stuff cached, right? And that's exactly true. You don't need to recompute these things over and over. You compute them typically once, and then the second time that you use them, you just fetch them again. Now, let's have a look at prompt caching and smart routing. So these are two very important concepts about this type of optimization that I just mentioned. Now, if you have thousands of users, and typically you do, especially when you reach this critical mass, that is like hundreds of millions of users using these services, okay? There is definitely, the chances that someone is typing what you are typing, semantically similar to what you're typing, are very, very high. So imagine this, if we are all asking, what's the weather today? What will be the weather tomorrow? Who's the president of the United States? These trivial questions that people ask, and much more than that, of course. Together with me typing this, there might be probably several thousand people, so several thousand requests asking exactly the same thing. Well, that's that's some room for improvement for a service, because if thousands of users share the same system prompt, well, the server caches the KV activations for that particular prompt, and so the next time I receive that request, I don't need to calculate that again. I just fetch it from the cache. Subsequent requests reuse, and they keep reusing the cached state, and so you can skip the recomputation every time, right? This will reduce, in fact, the costs at scale, because if there are 1,000 people doing that, you understand that you are cutting the costs by 1,000. Now imagine if there are millions of these requests in a minute or in a second, well, the costs that you are reducing are indeed substantial. Another thing, a very important concept that they use in production is called sticky routing. And this is a very nice one. It's a very nice piece of engineering and a nice finding, I would say, because if a user's request hits a different inference node, okay, nodes are these machines that are part of the cluster, okay? Why do we have multiple nodes? Is because we have to serve millions of people or more at the same time. So there is this horizontal scaling that you need. You need to spawn several instances of large language models because you want to serve more and more people, right? So you need more and more machines. Now these are nodes. Now if I keep hitting the same node, what happens is that I have many more chances of hitting a cache. So to find something in that cache and reuse it. If I keep changing nodes, well, when I migrate to another node, I might not find the same cache. I will definitely not find the same cache. And this means that I will have a cache miss. So in order to maximize the cache hits, what they do in the backend is like trying to route the requests of the same user to the same node. Why? Because they want you to enjoy exactly the same cache. Because the chances that you're going to continue the conversation is very high, which means that the chances of reusing whatever is in that cache are very high as well. And so the sticky routing is pretty much, it's a very smart way of reducing costs by not computing things and increase cache hits dramatically. I am not sure that they do based on IP and stuff. I'm pretty much sure that they use some kind of user hashing, or maybe your profile, your account, your email is kind of linked to a preferred list of nodes. So even when you change machines, it's very likely that your request ends up to the same node in the backend for that reason that I just explained, right? Now, there is also the prefill concept. Prefill means processing the full input prompt, which is also very computational intensive. And then there is the decode phase. These are the two tasks that a large language model system have to do. The decode basically is the token generation, one token at a time, which is also very intensive, but from the perspective of the memory bandwidth. Now, newer systems typically split these two. They use separate hardwares that are optimized for one task and the other separately, right? Now, let's talk about the elephant in the room here, memory. Because memory, as I explained at the beginning of this episode, is the one feature that really makes things look like human. Why? Is because if I, know about your past, about your feelings in the previous conversations, about your job, about your personal life, it looks like, oh my God, this AI is smart. It knows me. No, it's not smart at all. It's simply using some concept of memory which mimics the way we humans deal with memory. So how large language models remember things across sessions, even across different conversations, it sounds magic, but it's definitely not. And I'm telling you why. Well, first of all, the model does not remember anything, right? The model that you're chatting with is exactly the same model that another 500 million people are using. So how can that model be specialized on you? It's not. It's exactly the same model that is serving requests from very different people. What is happening is that after any conversation, there is typically a background process that analyzes that conversation, analyzes what was discussed, and pulls out what we call the salient facts, right? The important stuff. Think about job, things about your projects, your preferences, the color that you like, the cake that you ate, or the cake that you asked how to make, the recipe or whatever, technical background, definitely your demographics, your age, if you broke up with your ex-boyfriend or girlfriend, whatever. All that stuff is like a salient fact, and is part of your profile, right? Now, what is this? It's nothing more than text stored somewhere, right, in a separate store that we call memory. So all these facts now are stored as structured text in a simple database. Again, there's no magic, it's text and database. Now, what happens is that there is a kind of a lossy compression, right? In the sense that the tone that you explain these things, it disappears. The feelings, I don't know, all the things that it's just the raw fact. It's something very crude and very raw, right? So only the discrete facts survive, right? So these things are stored in a database. Now, what happens? How do I use these things? Well, it's very simple. At the start of each new conversation, these so-called salient facts, they are simply fetched from the database, and they are literally dropped into the system prompt. Remember this thing that I showed you here, the system prompt at the beginning. It's like, wow, it's like, it looks like magic. Well, it's no magic. There is a database that I fetched something from, and I made sure that the relevant facts are now part of the system prompt. And so now what happens is that, well, the generation of these tokens now will take these facts into account, and the answer looks like magic. Okay, so some memory architecture patterns. Again, we start from the simple way to the most sophisticated ones, or the ones that are currently used in production. The very naive way of a memory architecture pattern is so-called explicit fact extraction. What is that? Well, you extract key facts after each conversation, you store these facts as structured text, and then you retrieve and inject on the next conversation, session, whatever that is. It's a very simple concept. It's a very simple implementation as well. It is deterministic. It has low latency, as fast as fetching this stuff from a database is. This is exactly what, for example, systems like Claude AI Anthropic use. But I believe it's kind of, every system now are using these things. Another more sophisticated way of retrieving information from memory is the vector database. And we have discussed this many times, even on this show, and you find a ton of documentation now about these concepts. They are not new at all, not anymore. So this is essentially embedding concepts, okay, facts, memories, what we call memories, as vectors, all right? Now, what is a vector is the numerical representation of a word, a paragraph, an image, whatever piece of information can be converted into an embedded vector, and then this concept is represented as a vector of numbers. Now, what can you do with a vector of number? Well, that is something that you can do very simply with the linear algebra, which is calculating the similarity between two numerical vectors, okay? Cosine similarity, dot product, whatever. Now you use these things essentially to search for the relevant or the similar concepts in the embedded space. Okay, so these embedded memories are essentially vectors. You retrieve only the most semantically relevant chunks for the current query. You use your query, your prompt, as you essentially convert that into a vector as well, and then you use that vector to query into your vector database and fetch all the concepts that are in the database at that point. You fetch these things and you again inject them back into the system prompt. Does it sound magic? No, it's simply a nice piece of engineering. I mean, that's all it is. But it's not magic. Now, of course, this is much better because embedded systems have been proven to be much more performant because it's linear algebra, it's raw linear algebra, and there is also a very nice match between the semantic meaning hidden behind that concept that is pretty much represented quite well by numeric vectors. So it works. Now, there is also summarization chains. I think we have discussed this as in another episode long time ago at the beginning of the GPT frenzy. So this is essentially what Claude does. Even now, I experience that in person, which is periodically compressing old conversation segments into summaries. So You take something from the past, instead of injecting back into the next prompt over and over again, and so that the context window starts growing quite dramatically, you say, okay, look, let me compress what I've been saying, I've been conversing so far. I compress that into summaries, and I provide these summaries to my next conversation. Right? It's an optimization. Of course, you are losing information, you're losing a bunch of things, but all in all, it works. Especially if your conversation is relatively long and you keep appending, missing some details is okay, because overall, you're maintaining the big facts of the conversation, right? Now, you keep only the summary in the context, and of course, information loss is irreversible. Now, the good system is the one that compresses the things that are, let's say, less relevant to the conversation, because if you are compressing everything too much, you're losing too much, and then that injection becomes kind of irrelevant. Now, what happens in even more sophisticated systems is, in fact, hybrid. Okay, so this is the best practice so far, which is essentially a combination of all the three, right? So recent turns, the turns are like user turn, assistant turn, user turn, assistant turn, in a chatbot experience, right? So the recent turns are passed as they are, verbatim, plus older turns are summarized. So think about old memories, memory from far past. And then, of course, we have long-term facts, the things that you should never forget, right? Now, why this looks like magic is because, well, it looks like pretty much how human memory works, right? When you enter a room, you look around, and there are objects on the desk, on the chair is that position, the cat is on the shelves, whatever. You memorize these things, right? You have short-term memory. Then you get off the room, you go out for a running. You might have forgot that, all how the objects were placed in that room. Does your life change? That was an hallucination. No, your life doesn't change. It's typically not affected unless there are important things to remember, and then your brain kind of triggers and say, okay, if I have to, let's say, see my partner and say, I saw the phone on the desk, and that's an important information, then yes, I have to remember that I saw the phone on the desk. But it's probably irrelevant that I saw the computer at the usual place, right? So that's important in the short-term memory. It's not so much relevant in the mid and long-term memory. And of course, I don't want to forget my name and my age, okay? So this is long-term facts. So that's pretty much how the human brain works. I'm not giving an explanation of how the biology behind that works. I don't know it myself, but it's mimicking, these systems, this hybrid best practice is essentially mimicking, this separation of short, mid, and long-term memory. And that's why it sounds magic. It's not. It's just a trick, okay? It's an illusion. So here are some takeaways as the old good fashioned way of writing presentations, if people still do that. Remember, there was like first the outline, then something, and then the takeaways. So let's give the takeaways. Takeaway number one: models are stateless, all right? Large language models are stateless. And that's always been the case for many, many, many services on the internet. Internet services are usually stateless, okay? And why is that? It's because it's not convenient to make them stateful, because there are a lot of complications there. I'm not going to the details of why is that, but when you want to serve something at scale, you better have a stateless service. Every request sees only what's in the context window. There is no hidden session state, okay? That context window, of course, has to be populated with something if you're not explicitly writing that, and that's the magic of the application layer illusion, which is indeed filling in that context window from your past conversation or conversations. The app reconstructs and resends the full conversation history every single turn. There are optimizations, so you can avoid that, but that's exactly what happens. Then I covered the concept of KV caching and continuous batching. These are the key levers for serving efficiency at scale, right? Then you have smart routing that maximizes the cache hit rate. So when you continue a conversation from another machine, you are typically ending on the same node in the backend. You will never see that node, of course. You just have to trust me. And finally, long-term memory is a completely separate system that is typically implemented by a database, a simple database, okay? And what do you do on databases? Well, you do the three things that you do on every database. You extract, you store, and in this case, you also inject what you fetched into the system prompt. Of course, this is a lossy compression in the sense that you don't have a true recall of all the things that you have, all the facts that you have been producing, but it's good enough for typical conversations or human conversations. So behind every conversation you have ever had with an artificial intelligence, there is no ghost in the machine, there is no emerging consciousness, there's no digital mind, as they say, that understands you and stuff like that. There is a very large matrix of numbers, a cluster of expensive chips doing essentially linear algebra at extraordinary speed, and a lot of clever engineering to make the whole thing feel seamless. The intelligence, and I quote, is pattern matching at a scale that we have never seen before, but pattern matching nonetheless. That's it. The model doesn't think, it predicts, okay? It has no intentions, the model has no feelings, no sense of self. It is a sophisticated autocomplete system running on infrastructure that your 1990s self would definitely recognize. There are servers, there is memory, there is cache, network, request, response. These are the concepts that are behind these magical things, right? The reason it feels magical is not because something new has entered the world, as they want to convince us about. It's because the engineering is very good, and it's so good that seems are invisible. The stateless amnesia, okay, typical of stateless systems, is hidden by an application, typically your browser or your agent pipeline, whatever, that silently resends your entire conversation or instruction to rebuild that in order to optimize. The memory, and I quote, is a briefing document someone quietly slips under the door, right? And the personality, and I quote, is simply a system prompt. Strip away the UX, and what remains is the same stack that we have been building since the very first web server came online. It's just bigger, faster, and with a larger electricity bill. So the next time someone tells you AGI is around the corner, or that AI is becoming human, or that something profound is happening, ask them to explain the KV cache. Ask them where the context window ends. The answers are not mystical. They are, as they always been, engineering trade-offs. And that's not a disappointment. That's the whole point. I'll speak with you next time.